Hello everyone, this is Sakshi and I welcome you all to my edutech platform Way to Learn. So today we are going to solve some of the problems from mathematical physics and the topic today is Fourier series. So in my last two videos I had uh, spoken about Laplace transform and their properties. So today we are going to see Fourier series and in my next video we are going to see Fourier transforms. So let us start. So before we get to know what is Fourier series, the first thing we should know is the periodic function. So if the value of a function f of x repeats itself after an equal interval of time, then that particular function is said to be a periodic function. So it can be written as f of x is equal to f of x plus t, and that is at whatever interval at time t or 2t or 3t, the function will be same. So these are some of the examples, whereas sin x, cos x, cosecant x and secant x uh, have the same value at a time period of 2 pi, and tan x and cot x has the same value at time period of pi. So let us see what is Fourier series expansion. So a non-sinusoidal periodic function can be expressed by sum of set of sinusoidal oscillating functions or periodic functions. So this sum of two oscillating periodic functions are known as Fourier series expansion. So it is given as f of x is equal to a naught by 2 plus summation n is equal to 1 to infinity a n cos n pi x by L plus summation n is equal to 1 to infinity b n sin n pi x by L, where a naught, a n and b n are the Fourier coefficients. So these are some of the useful integrals where uh, these integrals can help you in solving your sum. So this is one of the first integral, and this is the second one. This is the third integral, and this is the fourth one. So the last one will be very much useful for you in order to solve any integral problem. So the important note here is that the intervals, that is b minus a, when you do upper limit minus lower limit, the answer should be 2l. So these integrals are valid for only for those upper limit and lower limit values. So let us see the Fourier coefficients, where I had told the a naught, a n and b n are Fourier coefficients. So there are various values of Fourier coefficients based on the interval. So if the function is defined in the interval minus L, L, then the Fourier coefficients are given as follows. So you can see the limits are from minus L to plus L, and there are three coefficients a naught, a n and b n, which is given as follows. So if you don't remember how to like memorize your a naught, a n and b n, you can see your Fourier expansion, whereas a n is supported by, that is, it is a coefficient of cos n by x. So an will have cos term. Similarly, bn will have sin term because it is the coefficient of sin n by x by L. So the only thing that vary here is your limit. So if the function is defined in the interval 0 to 2L, then you can use this. The change is only in your interval. And next, if your function is defined in the interval 0 to 2 pi by omega, then your Fourier expansion also changes as cos n omega t and sin n omega t. Similarly, your a n and b n will have cos n omega t and sin n omega t terms. And your limit is from 0 to 2 pi by omega. And the fourth one is if the interval is defined in minus pi by omega to pi by omega, it will again have cos n pi omega t and cos n omega t and sin n omega t. Similarly, your a n and b n will have the same terms and the limit will vary. So let us see the even function, or we can also say this as the half range cosine series. So for an even function, you know what is an even function? That is, if in a given function, you substitute x as minus x, and even after substituting your x as minus x, you get the same value of your function, then such kind of function is an even function. So for an even function, a0 will have this kind of value and an will have this kind of value. Bn will be 0. So for an even function, your Fourier expansion will not have your Bn term. And now for the odd function or half range sine series, which is also called as half range sine series. Here we know that odd function, like if you change the sign of your x, you're going to get the same value. You're not going to get the same value of your function. There will be a negative sign included in your function. So those kind of functions are called as odd function. And here your a0 will be 0 and an will be 0. Bn will only be present and your Fourier expansion will have only the third term, which is the Bn term. Let us see the Parseval's formula. This is also similar to, this is actually similar to the last formula that we saw. This is an easy way to remember all your formulas. If your question is solved by Parseval's theorem, you can use these formulas. So you can also see, make a note on the Fourier series in complex form. We don't have like much questions in exams from Fourier series, but we do have from Fourier transforms. So, but these Fourier series will be very much useful for those attending GATE exams. So make a note of these formulas. And then f of x is written as c naught. Instead of a naught, we have c naught, cn, and c minus n. And your cos and sine are written in exponential form. Your c naught, cn, and c minus n are given as follows. So let us see an example how to solve such kind of problems. So here I have a periodic function f of x of period 2 pi. That is, for every 2 pi, my answer will be the same. So, and it is defined by the given interval. The approximate Fourier series expansion for f of x is, so we have to find the Fourier series expansion. So let us see our Fourier expansion is given as this. So here, if you see my n pi, you have been seen that the Fourier expansion will have an cos n pi x by n. So here L is given as 2 pi. So on substituting that, you're going to get cos n x by, okay, cos nx and b in sin nx. Okay, then you can find your a naught by using your formula. You're going to get a naught to be 0. And then an can be solved using the same formula. So on integrating, you get an to be 0. And you'll have your bn, after integration, you'll have your bn to be 2 by pi n, 1 by minus 1 the whole power n. So if you see, you can say that your function is an odd function because your a0 and an are 0 and you have only bn. So you can say that that particular function is an odd function. And then now you have bn to be 2 by pi n, 1 minus 1 the whole power n. So bn will be 0 for even n and bn will be 4 by pi n for odd n. So we do not need 0. We need only a particular value. So our n should be odd. So only for odd n will have bn values. So we consider only the odd numbers, that is n is equal to 1, 3, 5 and so on for our Fourier expansion. So our Fourier expansion is now given as 4 by pi sin x plus 1 by 3 sin 3x plus 1 by pi sin 5x and so on. So if you get this, you are going to do this homework problem where I have given the function. It is similar to that previous problem and you have to find which option suits your Fourier expansion. So let us see the solution for our last problem, which was from Laplace transform, and I had given the function, okay, the Laplace transform of sin pi t was given as this, and I had asked to find the Laplace transform of t sin pi t. So you can directly use the property over here. So in the solution, I have used this property where L of x power n f of x is given as minus 1 the whole power n, differentiation with respect to s. So now the t power is 1. So I can use n to be 1. So on doing that and on differentiating this particular pi by s square plus pi square with respect to s, I get the following, and minus into minus will get me plus. So Laplace transform of t sin pi t is given as 2 pi s divided by s square plus pi square the whole square. So hope you understand this problem. So thank you. Like my videos, share my videos, and subscribe my channel, and not forget to hit the bell. So you can also see my next like mathematical physics playlist here, and you can also see the classical mechanics playlist, and I have been solving for previous year questions. You can also have a look on it. So thank you, see you tomorrow. Ta-da!